In this video, we're going to work through example 2 in section 8.5 on Taylor series and Taylor polynomials. So in part A, we're asked to build the Taylor series for the function ln of x centered at a equals 0. So to begin, let's just recall that form of the Taylor series. So I'm going to write it on my paper, but again, if you want to just look at your workbook, that's completely fine too. Okay, so then just as we did in example 1, we first need to compute all of these derivatives. So let's go ahead and do that. So we need, first of all, the value or the function f of x. We need the first derivative. We need the second derivative, third derivative, fourth derivative. And let's go ahead and just work out those first 5 terms here. Okay, so f of x for us in this example is ln of x. So then the first derivative, well, what's the first derivative of ln of x? That's just 1 over x. And we're just going to keep it as x to the negative 1, just because we're going to be taking more derivatives. And leaving that x with a power is going to be easier for us to take the derivative. All right, so what's the derivative of x to the negative 1? Well, that would just be negative x to the negative 2. Just recall that power rule. The third derivative would be negative times negative 2. And I'll just write that out. Negative, negative 2, x to the negative 3. So that would just be 2 x to the negative 3. And that fourth derivative would be 2 times negative 3 x to the negative 4, which would be 2, not 2, which would be negative 6 x to the negative 4. All right, so then what's the next step? Well, now we need to evaluate at x equals 1. So we're using our polynomial or our series to be centered at 1. So we're going to evaluate at x equals 1. So let's go ahead and do that. So that would look like f of 1, f prime of 1, f double prime of 1, f triple prime of 1, and then f fourth derivative of 1. So just plugging in 1 for each of our x's here. So we'd first just get ln of 1, which is just 0. Then we'd get 1 to the negative 1, which is just 1. Then we'd have negative 1 to the negative 2, which is just negative 1. And then we'd get 2 times 1 to the negative 3, which is just 2. And we'd get negative 6 times 1 to the negative 4th, which is just negative 6. So now we have a lot of what we need for those coefficients already. And I'll just highlight them so we have them here. Okay, so let's go ahead and create that Taylor series then. I'm going to do a little arrow there for the Taylor series for f of x equals ln of x centered at x equals 1 is, so I'm just going to look up here at the Taylor series form and plug in what I computed for these values of f, and then divide by the appropriate factorial, and then fill in my exponent of x. So what does that look like? So that looks like the following. So we have p of x is equal to 0 plus 1 over 1 factorial times x minus 1 now, plus negative 1 over 2 factorial x minus 1 squared, plus, I'm going to go ahead and start that over writing smaller, so just give me a moment. All right, so a little smaller so we can fit all the terms. And then finally, if I'm just carrying out to the fourth piece here, I would have negative 6 over 4 factorial times x minus 1 to the 4th. And so this would continue. So at this point, let's go ahead and simplify, because we don't need a lot of these extra terms because a lot of things will cancel out, simplify. So just simplifying here, this gives us, well, 0. We don't need to include that. 1 over 1 factorial is just 1. So that term just looks like x minus 1. Then negative 1 over 2 factorial is just negative 1/2. x minus 1 squared. And then 2 over 3 factorial, so 3 factorial is 6, so 2 over 6 just gives us 1/3. So it looks like plus 1/3 x minus 1 cubed plus, and then simplifying this last term, we would just get 1/4. Oops, and we're going to have a negative -1/4 times x minus 1 to the 4th. And again, I'm talking a lot here, so as you're listening, it might be hard to follow. So what I suggest you do is pause the video and work out the terms yourself first, so you have a really good sense of what's going on, and then watch the video once you have a solution so that you can really just compare your work at that point. Okay, so at this point, though, we have a simplified version of what that Taylor series looks like. I'm going to go ahead and box it up here because we're going to use that for part B. So for part B, we're told to use the Taylor polynomials P1, P2, P3 to approximate ln of 1.05. So notice 1.05 is very close to 1. And that's not just a coincidence. The reason why we centered our polynomial or our series around 1 is so that we can approximate our function when x is close to 1. Okay, so let's go ahead and do this, and then we'll compare our approximations with the calculator's value of ln of 1.05. Okay, so why don't we start here by computing the Taylor polynomials at 1.05. So we're going to compute p sub 1 of 1.05, p sub 2 of 1.05, p sub 3 of 1.05. And now here's also an excellent place for you to pause the video, work out these polynomial values on your own, and then continue watching to compare your work. All right, so notice here that p sub 1 is going to be the first two values of our Taylor series. So because that first term is just 0, we're just looking at x minus 1. So that would look like p sub 1 of 1.05 would be 1.05 minus 1. So that's not too bad. That's just going to be 0.05. So then our next polynomial is going to be these first two terms. So that's going up until the x squared term, or the x minus a squared term. So for us, that would look like 1.05 minus 1 minus 1/2 times 1.05 minus 1 squared. So if we compute that out, you can check this, we're going to get 0.04875. And now for p sub 3, we're going to look at the terms up to the cubed term. So that would look like 1.05 minus 1 minus 1/2 1.05 minus 1 squared plus 1/3 1.05 minus 1 cubed. If you compute that out, you should be getting 0.048797. We'll just leave it at that. Okay, so it looks like these values are approaching some number, 0.05, 0.0487, 0.04879. So let's check what the actual value of f of x is. So f of, and rather not f of x, but f of 1.05, which our f is ln, so ln of 1.05. So if we consult our calculator, you can check. You'll get an approximation, because this again is also going to be an infinitely non-repeating decimal. You're going to get something close to 0.048790, etc. So again, before finishing, let's just pause and reflect on what we did and what those values of the Taylor polynomial are. So what can we observe about those values of the Taylor polynomial compared to the value of f evaluated at 1.05? Well, these values here, we should notice, get closer and closer to the actual value of f evaluated at 1.05. So these Taylor polynomials do a pretty good job of approximating our function value when we use more and more terms. Shouldn't be a surprise. The Taylor series itself should match spot on with our function value evaluated at 1.05. Okay. Awesome work, everyone, going through these examples.